Shall I try again?
It's still connecting on YouTube, I think.
It's connecting. Okay, it's live now, right?
Is it? I don't see it yet.
Apparently now it works. Is that true? Is it Norbert saying this? Can people hear me fine on the website, on YouTube? Yeah, I think it works now. I can hear myself quite loudly now. Too loudly. No, I'm joking, it's fine now.
Okay, so then I think we restart. Very sorry about this. I hope you can hear me as well. Maybe
yes.
Now it's a different mic, so maybe my audio quality dropped, but generally it should work, and that's the best thing. And Martina and the other speakers are of course more important. So I will mute myself anyway, and let's start again. And I'm very, very sorry about this hiccup. Basically, I changed nothing. I just restarted the streaming software.
Well, that's sometimes all one needs to do. Turn it off and on again. Okay, shall we start now? And maybe if the link for YouTube has changed in the meantime, we can reshare the link to people. Even though people on the they will know that it's changed because one can see it on the channel, but just an extra information. Okay, so I'm very, very sorry for this delay. I hope it hasn't caused anyone too much trouble or inconveniences. These technical things sometimes are sudden and annoying. So I'm just going to start over and be very quick. I just want to say hello to everyone again, and thanks for everyone again to be here at this third edition of WeSST. We already introduced it one another, but just to repeat ourselves, my name is Martina Stella, and I'm a research fellow in Trieste, the ICTP Center. And together with Michael and Norbert, we've been organizing this third edition of WeSST, for which I will be the chairperson for today's seminars. Maybe very quickly, if new people have connected, Michael and Norbert can introduce themselves once again.
Yeah, hi, I am Norbert Bader. I'm a postdoctoral researcher at the Leibniz University Hanover in Germany, studying mainly EHL contexts, and welcome to you all.
And welcome from my side as well. I'm Michael Woloch from the University of Vienna. Usually I do high throughput simulations with DFT, and now I'm doing live streaming, and that apparently is much harder than what I usually do, because I managed to screw this up royally in the first half hour, but now it should work, and I wish you a good seminar.
Cool, thanks. I would never underestimate a YouTuber again. So I was going to say that this year theme that we have decided to choose for WeSST is to look at the hot topic of learning about tools based on big data, high throughput, machine learning, artificial intelligence, applied to tribology applications. We have seen that more and more people are getting interested in this topic and in mixing these two topics. So we put together a very nice lineup of speakers that could sort of introduce us to tribology application of machine learning, but also introduce us to the tools that we might want to use if we get really interested in doing that ourselves as well. So I was going to say that we took over Chiara Gattinoni and James Ewan for the organization of this web series last year, and we have slightly introduced us to. So I just wanted to give you some details about this. We have decided to have 3 separate days. The first day is today, the 30th of September. We have another day of seminars on the 10th of October. And finally, we have the last day of seminar on the 14th of October. On each of these days, we have 2 main invited speakers and 3 flash talks. We are going to, as you all learned by now, we are going to live stream everything on YouTube. Questions will be in the chat, and we're going to pick up the questions and give them to the speakers at the end of the sessions. We also take questions from the speakers, so they are in a Zoom separate room. So if the speakers also wants to have questions, they can write in the chat, they can raise hands, and we will take care of this. So without further ado, because we have already sort of been a bit delayed by technical issues, I'm going to go and present our first speaker. I'm very, very happy to see again and to introduce to you Luka Gringelli. Luka has a master in engineering, but he went to have a PhD in physics from University of Amsterdam. He joined the Fritz Haber Institute of Max Planck with Matthias Scheffler, where he was leading the group about ab initio statistical mechanics of clusters, catalysis, and corrosion until probably until 2015. And then since then, he has been leading the big data analytics for material science in Nomad laboratory, which is where we met actually, and which is now at Fritz Haber Institute and Humboldt universities. So he also contributes to coordinate the area of theory and computation in the Fermat Consortium at Humboldt University in Berlin. And with the Nomad laboratory, he leads the development and applications of methods based on compressed sensing, symbolic regression, subgroup discovery, deep learning, and all of these interesting tools that we're really looking forward to learn for big data in material science. But interestingly, is also focusing on methods that can get to interpretable models and can cope with also small data for training. So the title of his talk is in fact AI Ready Materials Science Fair Data, Methods and Infrastructure. And sorry again for the delay, please Luka, go on with your talk.
Thank you, Martina, for the introduction and for inviting me here. So I guess I try to share my screen now. I don't know why this is already on the second slide. Okay, so Martina's already mentioned my title. So Artificial Intelligence Ready Materials Science Fair Data, Methods and Infrastructure. There will be essentially totally no tribology in my talk. So I will focus on the infrastructure that we have been building for material science data, and most part of my talk would be about artificial intelligence method to analyze the data. So we'll go a little bit back and forth between methods and infrastructure, but then the second part of the talk, I would say I'm very focused on methods, hoping that they will be interesting to you, even though the applications are probably far from your current interest. So I like to start with a general introduction on the terminology in about big data and artificial intelligence tools and methods. So according to some people in the field, we are experiencing the fourth paradigm in science, where the first paradigm was pure empirical science prior to, let's say, scientific revolution in the early 1600s, where theory and experiments started playing together. So the so-called scientific method. And according to most, at some point in the second half of the past century, we started a third paradigm where computer simulation entered strongly into the set of tools that people use in science. In as much one can simulate systems for which something is known, but some observable are derived only by doing computer simulation more and more extensive. And the new kid in the block is the use of artificial intelligence in several aspects with scientific data, be it to speed up certain calculations or even more interesting to interpret some results that are not so easy to understand just by looking at them. And this is essentially the area where I'm most interested in, but I will be a bit more general at the beginning. So the idea of doing artificial intelligence on data somewhat requires that one is able to store properly the data in order to guarantee this called reproducibility. With reproducibility, I put together replicability and reproducibility, meaning that one can redo exactly the same thing or obtain similar results with similar settings. So the idea is that data should be fair, findable, accessible, interoperable, and reusable. And I've been working with and for building this infrastructure that is called Novel Material Discovery, that is online since the late 2014, where we deal so far with the computer, so atomistic simulation codes, and the normal infrastructure hosts raw input and output files from these calculations. Most of the data that you would find there are from DFT calculation at the moment, but we are expanding fast to force fields and say beyond DFT, excited states, and so on. The kind of original idea of the Nomad material discovery is that on one side we store exactly the input and output of the calculations, and then we have a way to map from this raw input output into an internal representation that is as much as possible independent of the code that was used to produce the data. And this so-called archive is the entity that is queried by an API that has been developed in our team, and allows for different levels of analysis of the data. Here summarized by this encyclopedia that is essentially the browser of the data, and the artificial intelligence toolkit that is the area where I am most active in the Nomad laboratory. So the toolkit, the artificial intelligence toolkit, is a web-based platform that hosts a curated set of Jupyter notebooks that allow people to analyze with artificial intelligence tools the data that are in the Nomad archive. So you find it at this link. In any case, if you have problems, just write to me to find what I'm talking about today. A current main developer of the toolkit, I want to give credit to Luigi Spilo, that has been working hard in the last, say, couple of years at the interface level, but also at the core level of the infrastructure, of the artificial intelligence toolkit infrastructure. And so I want to mention that the same thing that you would find online is also shipped to work independently on local machines, including a laptop. So you would have exactly the same software, and you could access the data in the Nomad archive exactly in the same way on your computer. So the purpose of this artificial intelligence toolkit is threefold. So on one side is giving direct access to the Nomad archive via our metadata schema that is called MetaInfo, and in order to perform directly artificial intelligence analysis on the data in a online Jupyter notebook, so one can directly try doing some analysis without need to install anything. Keeping the spirit, yeah, that's what they said. Yes, it is important that at this level, no registration is required. At the same time, we offer a library of hands-on tools in order to perform ready-made artificial intelligence analysis on some data. So just to showcase what one can do, and we balance between kind of textbook methods that one may find on, say, scikit-learn, so Python library, and method that we have introduced ourselves from the Nomad laboratory. And this is what I will be talking in the next part of the talk, these methods that are a bit unusual. And also the mission of the notebook, so of the toolkit, is to offer a platform where people can store essentially the analysis workflow done on ab initio data in order to perform, in order to reach some publication level results. So ideally, for each publication that has some artificial intelligence analysis on ab initio data or scale-based data, atomistic data in material science, one can produce a notebook and have it stored essentially fingerprinted, and then one gets a unique identifier, a DOI, to the notebook in order to have it as a sort of extended supplementary information to a publication, a very interactive one that hopefully helps people in going deep into what one has developed and obtained. So people can reproduce and very simply try something slightly different without need of lengthy re-implementations and so on. So we hope we are fostering the kind of boosting of reproducibility in at least computational material science. So the infrastructure is now expanding also to experimental data. But this is just at the beginning. So at the moment we are kind of strong on computational data. So this said, I would like to go into. Okay, sorry. This is just a snapshot. This is the entry page, and this would be a snapshot of the list of notebooks that one finds. With some kind of metadata on the notebook that tell which kind of method and system is being used and investigated. Okay, so rest of my talk is about methods that are implemented. So as a disclaimer, okay, let me go back. This can be distracting now. Methods that are so all the methods that we'll be talking about are available in the toolkit. That's why this lengthy introduction. So after this talk, if you are curious about some method and some details been a bit hard to grasp from my presentation, you just go to the related notebook, and you have plenty of time to go through all the detailed steps and understand what has been going on. Okay, so in order to introduce the methods that we have been developing, I make a very quick general introduction on artificial intelligence, just to be sure we are on the same page when I mention certain terms. So first of all, we have the big container that is called artificial intelligence. That is basically the set of all algorithms that in one way or another try to mimic human intelligence. So this is not necessarily related to learning, but every algorithm that makes decisions or tries to make predictions is called artificial intelligence, even if it is not trained. So the programmer really tries to guess all possibilities and implement a bit in a hard way all the models. Nowadays, this part of artificial intelligence is not much explored, but that's the big container of artificial intelligence. What one can subdivide artificial intelligence into, before I get to machine learning, that is of course the big word that everybody hears about, is that one can do essentially two very different types of analysis on data. That is the quite common, I would say, confirmatory analysis. When people talk about doing some artificial intelligence on some data, typically they have in mind some regression or classification model and the training of this regression or classification model. Quite interesting is also the so-called exploratory analysis that allows for exploring, interpreting data in a more free way. So it's not just trying to predict a specific value, but to have a representation of the data that suggests something to the user, to the scientist in this case. So I like to see this exploratory analysis as a nice companion to scientific research. Nope, the other direction. Okay, going to a little bit more standard classification. So as you see, I removed this classification because exploratory versus confirmatory is independent of, say, this other classification that is machine learning. So you could have machine learning in both subsets. And machine learning is the subset of artificial intelligence where algorithm learns. And learning means that the algorithm improve strictly the more data is provided to the algorithm to infer the model. Mathematically, this is done via a trick that is called regularization, and I will talk a little bit about regularization in the next part of the talk. But the important thing is that learning means really improving with more data. A subset of machine learning that has been, I would say, recognized only more recently is representation learning. Even though methods have been around, people started talking about representation learning only in the last few years, to my knowledge. And this is the set of algorithms that learn a representation together with a model. So there are a lot of machine learning algorithms in which one gives some input representation and the model is trained on that representation, meaning that there is some typically highly nonlinear function that is learned on the whole representation. But there are methods that kind of extract a representation out of the input that is given to the algorithm. Deep learning is clearly in this class. So for those of you that have been doing anything with deep learning, you might know that a deep network is learning an internal representation that typically is hidden in some of the so-called hidden layers. People do not need to access it, but sometimes exploring how the internal representation looks like gives some insight. We have done some work in this direction, but decided not to put it today. So I will focus on the so-called symbolic inference, that is a bit of unusual approach, and where we have made some, possibly a nice contribution that people can use also in Tribology, for example. So just to translate, inference is again a way to say learning from data, and symbolic is hinting at the fact that the models that are learned are explicit analytic equations. Now, of course, every model is eventually a set of at least mathematical expressions. But symbolic regression tries to do it in a transparent way, so to have a somewhat simple model that one can inspect and to some extent interpret, as I will try to show. So in this class we have symbolic regression classification and also another uncommon tool that is called subgroup discovery. Sorry, I was looking at if there was anything interesting in the chat, but it's just about the break. Okay. Okay. In any case, I guess Martina will interrupt me if there is any question that clearly you are free to interrupt me and ask at any moment. Okay, so let me go directly to this combination. So this symbolic inference with the first of the methods. The first approach is a combination of symbolic regression and compressed sensing, and then I'm explaining in this slide what I mean by that. So what is compressed sensing? The idea is to express a property of a system as a linear expansion over basis functions, that in physics is always a very nice idea. The basis functions here are nonlinear, or could also be linear, but typically are nonlinear functions of some input features that one kind of selects for the system at hand. So I will show some example, and this is the step where you need the kind of domain expert, as people say in machine learning. So you have to fancy a little bit what could be important. As I will try to explain, it is not super important that you guess everything correctly. So if you give some redundant features or completely unimportant features, the method is well equipped to neglect these features in a very clear way. So you will learn that some features are completely not important or redundant. If you miss features, then of course your model probably will not be very good, but also that you will see from by the performance of the model itself. So if this linear expansion here is truncated at very small number of coefficients, and still the performance of the model is quite good, we are in the realm of so-called compressed sensing. So mathematically is written as a kind of regression problem, so minimizing the difference between the known values of the property and the predicted one by the linear model, under a constraint that the number of non-zero coefficients in this expansion is as small as possible. This is what is known as compressed sensing. This is not always possible. You need that such representation exists. But if these nonlinear functions are created carefully, this representation typically emerges. And graphically, what we are doing is essentially to solve a linear system where the number of columns in the matrix, so essentially the number of basis functions in this expansion, is large, typically much larger than the number of data points. This is where this small data enters. And the thing works because we just allow few of the coefficients to be non-zero, and therefore we pick up columns in this matrix. So that this means that this expansion will be only few components, and this is in a nutshell what is compressed sensing. What is symbolic regression? Well, I already mentioned what it means, but as a word, but as an algorithm, it means that we construct a mathematical expression by combining features with operators. We have a vocabulary of operators, say starting from simple, some even linear ones, addition, powers and a set of elementary mathematical function. But here one can be as creative as one likes. And then these features are combined with the expressions, with the operators, to yield more and more complex expression. The reason why I represent it as a tree like this that you see here is that this is the way it is actually implemented in all symbolic regression codes. And this is a nice way to do it, because you can always substitute a node with a subtree and always get an expression that is mathematically well formed. And this is my engineer heart that suggested this, because everybody that's been working with an HP calculator knows what I'm talking about. Anyway, so the method in itself has this ugly name. I can say it because I invented the name, so I'm free to bash it. And it's called sure independent screening plus sparsifying operator. In short, SISO. There is no correlation with SISA in Trieste, but it just came up like that. So this is essentially everything I say about the method. I once more redirect you to this nice notebook done by one of my students on a tutorial introduction to the method, where we start from a simple linear regression and then introduce step by step all the ingredients of the fully fledged method, including the recently published C++ code, very efficient to perform this method. And the only extra thing I want to say about this method is that it has a built-in way to determine the complexity of the model. So the complexity comes in two terms. One is the depth of this symbolic tree, so how many layers you have in the tree when you generate it, and the number of these active dimensions. So in this linear expansion, how many dimensions are different from zero. And the methodology as a way to determine the optimal complexity and stop when that is reached. Okay, slowly going towards applications. So the purpose of this approach, one of the main purposes, and this is why we get this, we insist on the linear expansion, is that we are aiming at materials maps. So representation of the material space, where materials are points that described by a certain descriptor. And then you get possibly classification. So points landing in some part of the map are crystallized in this example as zinc blende or as rock salts. And then you can have more classifications and also maps of continuous properties, like you are interested in absorption energy, and certain set of materials have, say, CO2 absorbed in a range of interest for, say, catalytic behavior. But the common idea is that we would like to have this representation that is low dimensional and somewhat inspectable, ideally two-dimensional. But of course, it could be higher dimensional. The complexity, as I was saying, is determined by the method, by the data, and by the system itself. So a kind of showcase application that I start to show is this one of the first we made, that is trying to find a simple descriptor for predicting whether materials with the chemical formula ABX3 would crystallize or not as perovskite. So perovskite is this crystal here, where you have this cubic arrangement of octaedra. In the middle, you have kind of the big cation, normally A, and then the small cations in the center of the octaedra, and then the vertices of the octaedra are the anion atoms. That's it, yeah, in this arrangement. And historically, this guy Goldschmidt, essentially 100 years ago, came up with this simple descriptor to predict whether a material would be perovskite or not. The input is for each isolated atom, so an information that you know about the material, the chemical element, the moment you select it for testing whether it would build perovskite or not, is this so-called Ionic Radius. I don't need to say now what exactly this is. It's just something that you can look up in a table, so you have the periodic table of this Ionic Radius. So with this descriptor, if materials end up in this interval here, they are predicted to be perovskite. And the accuracy of this prediction is fairly good, but not super exciting, especially if the anion is not oxygen. To be honest, Carl Schmitt was thinking about perovskite oxides, but okay. So we wanted to know if we can learn a better descriptor by applying our method instead of just doing trial and error. Essentially, trial and error is done by the machine itself. And we came up with a more complicated descriptor, but the ingredients are exactly the same. So this radii, this oxidation state is also part of the definition of this ionic radii. And just looking at the harsh split at a certain optimal threshold, this descriptor has a very good accuracy in prediction. I'm talking about prediction, but it is even nicer that the moment you define a kind of uncertainty interval, everything that is outside this interval is predicted with 100% accuracy. And in between, one can define, we did define a probability to be or not perovskite. So we end up with a continuous mapping. And this allows us to build what we were looking for, this materials map. So if we use the A and B material in terms of the radii as descriptor, we have this learned equation, and then we have that material in blue are predicted to be perovskite, in red they are predicted not to be perovskite, and in between you have this uncertainty region, and the material here are those that are known already to be not perovskites, and the model works very, very nicely. By looking at the way this formula is done, we can also be brave and say, what if we can analyze also double perovskite, assuming that there is some kind of averaging going on when trying to build a double perovskite that has two types of B cation in the center of the octaeder. They don't need to be ordered, like in this picture here. So we say, what if we just take the average between the D and B prime cation and make prediction? You use exactly the same formula without retraining. This complicated metrics just say that whenever we predicted something to be perovskite with this more complex formula, we were right, and we predicted thousands of new double perovskites. Some of them, in the meanwhile, since 2019, were also synthesized. This say application is, as I was saying, a notebook. So I'm just showing quickly that there is a notebook for in reproduced results, and this is called finding tolerance factor to predict perovskite stability with CISO. This will be the entry screen to the notebook, and one of the results of the notebook is that you would be able to draw interactively these maps here. So this is a snapshot from the notebook that obviously uses exactly the same library that we use for the paper. So that's why it looks so similar. But the thing is that you can do it on the fly, and then you have different data, and you have you want to look for different properties. You can just modify on the fly a notebook and try your ideas. Okay, now I will go by more and more complexity. So one to me very interesting extension that we did of this CISO method is the extension to multitask learning. So mathematically, the idea is that we learn different properties at once, but by imposing to use the same descriptor. As I mentioned, so in the single task CISO, this ST CISO, learning the descriptor means that we identify the columns in the matrix in our linear problem. having a multitask means that we identify the same columns, but the properties are changing. Furthermore, these gray areas here signify the situation in which data are incomplete. So we don't have all properties known for all materials in the training set. This is not something we invented. People have been doing multitask learning for quite a while, and it has always this stream robustness problem. So you can, if you don't have enough data to train one property, train more properties under the constraint that the model is the same. And then you will so kind of impose robustness to the model, and you can achieve a fine model with relatively small data. Again, mathematically, this looks like property 1 is a function of, so the descriptor is the same, but the learn coefficient in the linear regression can change and will change. So this is how it looks like. So one can summarize this by saying that the coefficient itself in the linear expansion depends on the way you index, in some sense, the different tasks. So you could have a finite set of tasks that I will try now to exemplify a little bit. And then you have that the coefficient depends on kind of the enumeration of the tasks. Or you could have also a continuous set of tasks. And this will be, as I will show, the most interesting extension. So the kind of straightforward application is when we have a finite set of tasks. Let's say that we are learning the formation energy for the same chemical composition in different crystal phases, because we are after constructing a kind of material phase diagram in which we want to predict what will be the most stable crystal phases given the formula. So this works. And the fact that we impose the same descriptor allows us to really draw the phase diagrams. This is for octet binaries when we predict when they crystallize as zinc blende, rock salt, cesium chloride, and there are other phases that would not appear in the phase diagram, but they could be metastable. Like this would be a cut of the same plot. Even when rock salt is more stable, this nickel arsenide in some regions is very close in energy, so one can expect to have metastable phases. So you have a full prediction on relative stability of materials on the basis of their chemical formula. So all these radii, and this is the distance of the dimers, are properties of the isolated atoms or small molecules that can be looked up in a database. So you don't have to construct the material in order to know which which crystalline phase will be more stable. So in this case, essentially the index that goes through the different tasks kind of summarize the different structures themselves in a kind of implicit way. So we would have that the model is the same for all crystal phases, and then we have different prediction for different crystal phases. Now, a situation in which we have a continuous property could be, for example, let me go back here, a situation in which we have the same material at different temperatures. So temperature is a continuous property, and if we sample the material at different temperatures, we can say that each temperature is a task in this formalism. But then we would have that the coefficient could evolve, the coefficients could evolve smoothly from one temperature to the other. And this is exactly what we achieved in this kind of very nice application we published last year in heterogeneous catalysis. So we are going really to real materials and real kind of problems. So we were after this kind of simplified chemical reaction. Actually, the actual network is here, and we inorganic chemists as well as organic like to pick up a few of them to say, okay, we are after this kind of oxidation reaction, and we would like to see whether we can learn a model by knowing the behavior of these 9 vanadium-based catalysts. So you heard correctly, we have 9 data points, and we want to learn a model on these 9 data points. So these are known catalysts. And this is a pure experimental effort. So in the group of Robert Schlögel at the Fritz Haber Institute, people did a tour de force in experimenting, characterizing material before the reaction, during the reaction, after the reaction, and so on, so that we have a lot of properties from the same material measured in a very consistent way. And then we are after finding, for example, I will show here the selectivity in producing acrylic acid, assuming that acrylic acid is a product that we like to obtain. I'm told by inorganic chemists that it's the case for constructing olefins. So you start with acrylic acid, and the selectivity towards this reaction is so the high selectivity is welcome. And the model that is constructed is a simple model with just two components that depends on temperature, right? So the material is described by a fixed set of parameters, so the descriptor, but the coefficient in order to predict the selectivity depends on temperature. Okay, and this is the behavior of the coefficient as a function of temperatures, and they go opposite in order to catch the effect. Different materials have very different behavior in terms of their selectivity. This would be the map if we collapse the descriptor into one dimension and have the temperature as another dimension, and we have these ISO curves of equal selectivity. So this material would be the winner with the high selectivity in this region. But we can do much more. When we have seen the model, we say, okay, let's see what constitutes the model. So this descriptor is a function of some mesoscale properties, like the pore volume of the real catalyst in a real reactor. So we can measure the pore fraction, or we can measure more electronic properties, like the activation energies of conductivity, its work function, and so on. They appear here. And then one can say, let's assume that we can manipulate the material in order to change some of these properties. So the pore fraction, for example, can be more or less easily manipulated by synthesis, and also some treatment can change the this activation energy of the bulk conductivity. And so one can basically change this material here and go to a much more selective material that maybe is much less costly than this other one. So at the moment, this is not part of this investigation, but this is just to say, train a model that one can inspect, see what are the relevant parameters, and then try to intervene on the material in order to improve it. Okay, it's about 5 minutes, right? Yeah. Okay, I can wrap up in 5 minutes. Maybe I skip this one. I want to make an interesting point here. So, if the model is not particularly simple, we have designed also a strategy to kind of statistically, so doing some statistical analysis on the model itself in order to learn a little bit more what is important and what is less important in the model. So in this case, I spare you the mathematical part. I go directly to the application, hoping that it's interesting enough. And then there is also a notebook, of course, also for this application and development. So the idea is that we were modeling the lattice thermal conductivity. We start from 75 materials from which we have experimental data on the thermal conductivity, but we can also characterize them from a computational point of view. So this is combined computational and experimental kind of learning procedure. So this is our model. So we make the prediction, and this is our ground truth. The model is trained on the logarithms of the conductivity because it spans several orders of magnitude. And the model, as usual, is a linear expansion. And then it is, okay, fairly simple, but not the simplest one can imagine. There are several ingredients coming in. And one would like to understand how to identify the leading parameters in order to, for example, screen materials and identify which one have large, or particularly large or particularly small thermal conductivity. To do that, as usual, when there is something mathematical and that you want to do on something, go to some Russian mathematician. For sure, there is a Russian mathematician that has solved your problem, and this is the case also here. Sobol has solved our problem, even though it has been discovered a few times. And so there is a way to do some kind of sensitivity analysis that is an ensemble sensitivity analysis. Normally, sensitivity analysis is done feature by feature, and this statistical approach by Sobol allows one to look at the interrelationships among features. So if we apply these indexes to our model, we find that only 3 of the features play a leading role. And I'm going to say what they are because it is important for the conclusion. That is the molar volume. Vm is the molar volume of the material. Theta d infinite is the infinite temperature limit of the by temperature. In practice, it is related to the spread of the phonon eigenvalues. So it's a static calculation on using phonons that gives us this number. And this sigma A is an anharmonicity index that requires to do molecular dynamics trajectory and essentially compare how much the potential energy source is not harmonic. So this is just a number that comes out of certain analysis. But just for you to understand, so this is related to the lattice constant. You just need to find the equilibrium lattice constant of your material. Here you need to do a phonon calculation, harmonic phonons, okay, involved but doable. And here this requires molecular dynamics in order to assess the size of this property. Now we say we set up the challenge that we want to find materials that have low thermal conductivity, and we see by looking at the, say, 3D basically manifold onto which this material live, if we consider only these 3 input parameters, that the materials that have low thermal conductivity have low lattice constant, molar volume, large by temperature, and small, probably it's the opposite. Anyway, and small anharmonicity factor. Yeah, okay, I actually can see. Yeah, it's exactly small, small and large. Anyway, so this observation suggests that one can set up a high throughput search in which one first looks at structural information, so the lattice constant, then harmonic information, and then anharmonic information. So I'm pretty sure you have seen these kind of high throughput funnels over and over. They were introduced probably in our field. I mean, I've seen them the first time in works from materials project. The novelty here is that when we start the investigation, we have no idea how to build the funnel. So we have these 75 materials, and the main output of building a machine learning model is not the predictive model in itself. It's the fact that it tells us that if you screen for some simple structural properties, and then in cascade on anharmonic properties, and then on anharmonic properties, you reach your desired result. So this is a kind of nice side effect of a simple model that it can be somewhat inspected and interpreted. But it turned out to be here our main results. So because we constructed to do that, and I'm confident that you can do this kind of analysis on very different systems. So essentially, I close here. If I manage to jump to the last slide, because I have a few other slides. Yes. And this is just the acknowledgement, and I arrived. So you have not seen one topic, but that's fine. So I would like to acknowledge all these people. Jan Vibra that introduced us to the marvels of compressed sensing and symbolic regression, and then Lucas Foppa doing some of this application. And okay, is completely missing one important person, Thomas Purcell, that made the last thing that I presented, and then of course Matthias Schäfer, who has been behind all these activities all the time. I thank you for your attention.
Thank you, Luca, for your very nice talk. Maybe we can give you a round of virtual applause. You know, Zoom allows that, so I'm gonna do that. There you go. Thank you very much. It was a very, very nice talk. We have already a couple of questions from, so please, the speakers, feel free to write.
So I stopped sharing, but I can go back any moment in case.
Yeah. So for the speakers, feel free to either raise your hand or write your questions in the chat. I'm going to start reading the first one I see here. I think it's from Norbert, who can ask it himself or I read it. If that's fine, I will read it. He's asking how sensitive are the methods to differences, uncertainties in measurements forming the databases for training.
Okay, yes, thanks. That's a very good point. I didn't go into these details. I mean, details, not very much details. This is the core of the matter, but they would require another half an hour explanation. This kind of this compressed sensing device is particularly tuned to be very robust to perturbations in the properties, so what you want to predict, but also in the values of the features, because you have a source of errors on both sides, right? Especially if the features that you plug in, like this an harmonic factor comes from some lengthy simulation, or they come from some measurement. So in general, the method is quite robust. Mathematically, this is because the number of say free coefficients that are trained is by construction very small. So the model tends not to overfit. In any case, as I mentioned, the complexity of the model is determined by the data themselves. So if you have more data, you may have more complex models. In any case, essentially the robustness is built in by the training procedure, because we already do this cross-validation in order to kind of assess that the selected descriptor is stable enough. Otherwise, you get the signature that the model has not enough data to make it short.
Okay, there is a question from the chat. Maybe I can ask that. That's from Stefan Peters. General question. As the big data approaches, parentheses forced paradigm, as mentioned in the beginning, are becoming more and more established, will this forced paradigm completely take over the third paradigm soon?
The third paradigm. So the third paradigm. Yeah, sorry, I don't even know if it is the right pronunciation. Sorry, I didn't mean to correct you.
Oh, correct.
So the third being the say computer simulation aided. Yeah, I'm not sure. Meaning that it depends on the question that you ask. The third paradigm was really yes, simulating say a complex system, say a liquid or something, in order to infer some properties. Now you can say yes. Now we do with the third paradigm. We try to predict directly the property without doing the simulation. I sense that that is not always possible. That in some cases the complexity is such that you are not able to derive a closed model to predict the property. In the same way, people were not able to derive closed model to predict properties in complex systems, say hard spheres, the famous first application of computer simulation in atomistic system. Oh well, the same in statistical mechanics. So nobody was able to even predict if there was a phase transition in hard spheres, and you needed computer simulation to do that. So you have a new system, you have some kind of strange matter situation with correlated electrons and so on. You may want to do computer simulation with an accurate model rather than doing the artificial intelligence part. What I see is that probably even the majority of the field is trying to use machine learning to speed up the traditional simulation, say molecular dynamics, Monte Carlo thing. So both on the model itself, so you have this so-called surrogate potentials, like things the main people would be Caborciani in Cambridge and Jörg Beller. Don't remember now where he is because he just moved. I think he's in Bochum. So with neural networks or kernel Gaussian processes. So this would be just potentials that are faster than the DFT that you trained on, or even a higher level. Or you could have better schemes for molecular dynamics and Monte Carlo, such that you can kind of guess what is happening next, and so on. So artificial intelligence is invading every subfield. I would say today I presented clearly only a part, but I don't believe that will completely override the third paradigm, so the simulation, and certainly will never override theory and experiments, most importantly. In a talk I gave a few weeks ago, somebody was very worried when I showed that you have this scale of paradigm, and then, okay, but then we forget about experiments. No, absolutely. It's an empirical science. We need experiments always.
Cool, true. And actually, we have one more question, and I think we have time for one and maybe one smaller question. We have one from Norbert again, who's asking something related to this. It says, if I understood correctly, some of the predictions are actually based on some sort of existing physical model, for instance, thermal conductivity. Now, how likely or easy it is to find physical models behavior if I just feed my AI with experimental data? Example, fluid data to find rheological models.
So that's a very kind of focused question. I would say you're right. So there must be a model, and that model must be somewhat simple, so that it can be reached by the complexity of this strategy. Clearly, you can have more complexity if you have more data. So, but at some point you hit a little bit of a limit. Typically, it's the memory that hits back you, because you have to create all these possible models. And I believe that there will be many situations in which there is a not so complex model, let's say, even for very complex situations like rheological data. I think one should just try. I mean, at the end of the day, if you have a good data set to start with, it is relatively easy to set up the thing and try with the features that you may fancy. What you gain extra than training a neural network is that you need typically way fewer data, and then you can look in what you've found and then see if that gives you some hint on how to actually derive for first principle a model. or at least it gives you an idea on which are the main parameters and how they play a role. But by all means, I think there is plenty of models that are just a little beyond our human capability at the moment, at this moment of evolution. But yeah, they can be derived by a method like this symbolic regression. Thanks.
Okay, thanks. Now a very small question from me, just because I'm curious. So from the last couple of applications that you've showed some combination of experimental data and tools for machine learning. And you said that there are some notebooks on this too?
Yes.
Meaning that there are experimental data now on the Nomad repository?
Yeah. Okay. No, so the
What's that?
No, the notebooks, they have the data, let's say, has data together with the notebook. So they are stored specifically for that notebook. We are working hard on having already something usable from experimental data. So there is the whole part of Fermat that is working on metadata for experimental data. The first one that should appear is it the one that I showed? Yes. So this catalysis kind of project. The notebook is not yet released. It will be soon. And that will have the data already arranged in the way
it will be parsed.
It will be the future of Fermat. So these are still only this data, so you will not easily find more, but they are already tabulated and stored in the proper Fermat form. So yes, that will give you an example on how we are going to do that. The coordinator of I just close quickly. The coordinator of the experimental is working hard to get actually the data into the archive. We'll keep you informed what we get.
Fantastic.
And
thank you, Luca. So if we can thank Luca again for first of all waiting a little bit longer than he should have, and for his talk. Okay, Mika, do you want to say something?
No, I just wanted to
or
say
I can move on.
Peters was very happy also with the talk, and that his question was very satisfactorily answered. And yeah, I wanted to say that this is the perfect point to go to the next talk, I think.
Yes, exactly.
Yeah, very good connection.
So we are going to the second part of this seminar series, which is the part where we have the flash talks. Just very briefly, we had this idea of introducing shorter talks where we're going to have 3 people. They're going to have a 10-minute presentation, each of them. And they're going to go one after the other. So we will wait at the end of the 3 flash talks to then ask questions in the same format that we have just done with Luca. So both the chat on YouTube and on Zoom. So the 3 speakers in the order that we have are Nick Garabedian from KIT. He's a Humboldt postdoctoral fellow and a group leader. His title is Big Open Data in Tribology, Big Open Data in Experimental Science. So perfect link to what I was asking as well. He will be followed by a colleague of his, which is Ilya Bago from KIT as well. He will talk about give tribological data a meaning, Vocabularies and PIDs. And finally, we have Ebru Chihan from TU Dresden. She's a postdoctoral research fellow, and she's going to talk about fingerprint of a structural phase transition during super lubric sliding. So as I said, let's go one after the other. So once Nick has finished, we will just continue. Please, Nick, you can go.
And sorry to interrupt quickly. Because we have started late, we have decided to skip the break that was initially scheduled for after the flash talks Q&A. So there will be, after the 3 talks finish, 15 minutes time to ask questions and give answers. But the 15 minutes break that should have been after that will be cancelled. So we only are 15 minutes late and not 30. And again, my sincere apologies for this problems with the audio in the beginning. So then, Nick, stage is yours. Thank you.
Thank you very much, Martin and Michael. I hope everybody's seeing my screen. Yes, I see the thumbs up, Martina. Thank you. Thanks for the introduction. And yes, my name is Nick, and I'm currently a group leader of linked tribological data at the Karlsruhe Institute of Technology. My background is in experimental nanotribology. That's my PhD. And since then, I've taken sort of a pivot towards data and big data. So we all know that investments in science have brought us unimaginable, exponentially growing economic prosperity. However, the way to conduct science has also has to evolve and improve over time. So our journey to start dealing with big open data took us to the point where it came from the desire to find a united solution to some of the existing and future challenges that we face. So the story goes the following way. We were for some time we were wondering how can we become a next generation research lab, and we defined a few metrics through which we could achieve that. And one of them was we wanted to preserve our data better. We wanted to accelerate the lab operations just in general from a managerial standpoint. We wanted to be able to share our data more efficiently within the lab and outside of the lab. And finally, we wanted to enable our data for machine learning. Now, because big data has 1,000 definitions probably, a more specific and somewhat actionable goal for us became FAIR data. And to those of you that are hearing this for the first time, FAIR data is an acronym of findability, accessibility, interoperability, and reusability, which are a set of principles and guidelines to observe when dealing with data. And the overall outcome of using these is that communication with other researchers becomes easier. The information and the data that is provided in a fair manner becomes machine actionable. And last but not least, something that I see often, not mentioned often enough, I think, is the fact that once data is organized better and it's findable, more findable, then the need for repeating already performed experiments goes down. Thus, we avoid wasting very valuable scientific resources. So with these things in mind, what we did about a year and a half ago was to do a proof of concept where we conducted a somewhat standard showcase experiment of lubricated contact of metal against metal contact. And we basically asked the questions, can we do this experiment fairly? And what is fair for tribology? The results of all this are summarized in 2 publications that came out this year, and the data is openly accessible with the metadata accompanying it, with an ontology that connects the data inside and the metadata, and this is freely available. You can find this in the publications. However, without going much deeper into the publication and all the work it took to define 3,000 terms or so at some point, the major outcome of all this was that we realized that it's a known fact in tribology that a lot of the most of the tribological performance of materials comes from the surface preparation. So really big data in tribology is becoming big data of sample preparation or so. Of course, the experiment has to be accounted for, but the sample preparation and all the different types of processes becomes really central to the whole problem. So with this knowledge in mind, we shifted towards asking ourselves, how can we make FAIR data a daily way of conducting science in the lab? So the new framework that we operate under looks like this. That is probably a little crowded, so I will actually run this through a few stories. So the first story is about a PI who wants to make their data open, given some governmental or funding requirements or self-motivation. Now, maybe this PI will go to an electronic lab notebook provider to help with that. And there are many solutions for electronic lab notebooks. Many of them work really well. and they're great for organizing the results of scientific work. Now, having your data in an electronic lab notebook, it makes it very easy to share to an open repository. However, the problem here is that electronic lab notebooks organize the results, and it is somewhat challenging to give richer meaning to the inputs to the electronic lab notebook. And here's where our Vocpopuli solution comes in. This is going to be described in the next flash talk, but basically this is a controlled vocabulary management tool which enables the creation, curation, management of metadata, the pieces of data that describe the data. And this is what, to us, opens the door for big data and really scalable machine learning. So the vocabularies in Vocpopuli can feed into the electronic lab notebooks, which then can make the data open. And this yellow arrow over there is where I believe we can make the data truly fair, as it is a requirement by the FAIR principles to have fair vocabularies associated with the data. In the next story, well, I have a quick preview of what Vocpopuli looks like, but it is a glossary of terms. Here you see for a block specimen that you can hierarchically describe it with its general information like location, operators in charge, and so on and so on. There are hundreds of these descriptors which we assemble through the process that is part of Vocpopuli. Now, another user story here would be a curious student, newcomer to the lab, who wants to do machine learning on the data. Well, here they would need something like an ontology. And for this, we have the solution called OntoFairCook, which it is in its early development right now. But essentially, it enables the metadata to be fully connected before it goes in the electronic lab notebook, and thus enables machine learning. I need to say that these two are currently part of a project called MetaCook, which is funded by the Helmholtz Metadata Collaboration. And we have collaborators from 3 more labs sitting in another institute in the north of Germany called Hirion. So we are testing our solutions as we're developing them. Another user story now would be of another student who is in the early stages of their bachelor's degree, who would like to learn about the lab's operations. So with this, here again, we can think about the vocabularies that were developed in Vocpopuli as a place where newcomers to the lab can find a description of the procedures that take place in a lab, and thus become an easy entry point to any new student. So the vocabulary is really, once a scientific group gets together and puts their thoughts into organizing what they talk about on a daily basis in a structured manner, it's a game changer for the entire operations of the lab, and it makes things more efficient. The last point on this slide would be the so-called FAIR-Safe package of solutions, which we're also developing. These also feed from the vocabularies, and they basically make the whole process reliable by integrating with, say, the manual process in a tribology lab, like polishing a sample. Now having a vocabulary makes it very easy to construct an application called FS Digital Book, where you can make everything on the front panel of a tablet so that it's easy to use next to your grinding or polishing machine. You can also, using these schemas from Vocpopuli, you can use a validator to make sure that the data that is stored in the results management systems of any of the electronic lab notebooks is within the schema that is prescribed before publishing it in an open way. And there are other solutions as well which interact with the regular work of experimental scientists. And just to reiterate, once again, we believe that everything starts at Vocpopuli or similar solutions for metadata management. And we are not trying to replace electronic lab notebooks. I think they are doing a great job, but actually we're trying to help the adoption of electronic lab notebooks by making it easier for users to become digitalized. And the results, basically, it takes, at this point, takes about 2 minutes from the results, for the results from the tribometer to be uploaded to our ELN so that I can see them on my phone anywhere in the world. And it makes it easy to trace back accidents and correct for them because all the metadata is stored automatically. This all took us about 2 years to set up. Now, we've done the heavy lifting. I would say that with the outputs, it can take from hours to months, depending on the goals, to set up in another lab. So was this all worth it? I would say yes, absolutely. Thank you very much for your attention, and I'll be looking forward to your questions after my talk, or after the next 2 talks.
Thank you, Nick. We can go on to Ilya's talk. And also, yes, applause.
Sure. Thank you, everyone. Let me just share my screen with you. I hope, meanwhile, that the audio is okay. You can see me. That seems to be the case. Cool. Well, obviously, this talk is going to build upon quite a lot of what Nick just showed us. But before I start, just a quick introduction on my end. So I'm Ilya. I work in Nick's group at the KIT, the Karlsruhe Institute of Technology, and I am tasked with leading the software development of the tools which he just mentioned. Now, this presentation will dive a bit more in the technical side of the previous one, when here I will focus mainly on Vocpopuli, which is, so to speak, the central part of our framework. Now, we use Vocpopuli to basically answer the question, how do we teach a computer to think? Or in a more technical manner, how do we generate fair machine-readable data and metadata with the help of controlled vocabularies? Now, before I dive into Vocpopuli itself, I first wanted to start with 2 simple definitions. The first one being that of controlled vocabularies, or at least the way which we see them in our group. Now, controlled vocabularies are basically lists of terms. These terms can have hierarchical relationships with one another, and they also have definitions, as well as some additional information, like, for example, synonyms, data types, if those terms are later to be converted into ELN records, and so on. Controlled vocabularies are used to define and describe the relations between entities in a given domain. However, this is done in a fairly basic and simple manner, I would say, which isn't necessarily bad. A more detailed description of a given domain can be achieved with the help of ontologies. Now, ontologies also describe the relations between entities in a domain. However, these relations aren't limited to hierarchical ones. They can be as richly defined as the user or the developer of the ontology wants to. The tools which we use to work and develop, with and develop controlled vocabularies and ontologies are Vocpopuli on one hand, and OntFairCook on the other one. Now, the interesting point and thing is that controlled vocabularies can actually be converted into ontologies in a semi-supervised fashion, but the prerequisite for this is that the vocabularies themselves have been developed according to some best practices in the domain. Now, moving on, and maybe just again as a quick overview, this is the Karlsruhe lab framework. This presentation will focus on Vocpopuli, and yeah, that's all I want to say here. Now, what I will show you next is just a small video demonstration of some of the basic use cases, features, and so on of Vocpopuli. This here would be the first screen which a person would see. Now, you can see here that it says login with GitLab, and the reason for this is that that Vocpopuli is basically, and speaking in a very basic fashion, a front end for GitLab. So all of the vocabulary development which happens with the help of Vocpopuli is also mirrored in the background in GitLab, and in the form of different GitLab repositories, basically we have one repository set up for each of the vocabularies, which people can develop with Vocpopuli. The first step when logging in to the tool is to choose a vocabulary which one would like to edit. In this case, this is the cup grinding vocabulary. Now, I won't go into details about the semantics of each of the terms here, but you can see that they are structured in a hierarchical fashion. Each one of the terms has a data type associated with it. The reason for this is that these terms can be looked at as metadata fields, which can later on be exported into electronic lab notebooks. And yeah, here you can see a different data types. So we have dictionaries, strings, individuals, and so on. Now, a very basic use case, I would say, is that of adding new terms to the vocabulary. This can be done fairly simply. For example, using the Add New Child Term button, which opens up this form. Now here, I wanted to add the term student trainee to the vocabulary. Student trainee is just a kind of user role. As soon as I clicked on Add New Child Term, this form came up. And here you can see the different kinds of information which one can input per given term. So the first one is the term name itself. Afterwards, you can choose an individual, a data type, which in this case would be individual. Following this, a person can input the definition of the term. And this is actually a required element, so a person must input the definition. And then the additional fields which you see here are, for example, synonyms and translations. And also basically the different ways in which the newly defined term can be related to the terms which are already present in the vocabulary. So, for example, here on the left side, you can add relatively broader terms to the one which is being defined. That is to say, those terms chosen here are the ones to which the newly defined term is a subterm of. Now, that's a lot of terms there, but that's basically the gist of it. And we also have so-called related terms, which are related to the one being defined, but not in a hierarchical fashion. Now, as soon as the term has been submitted, it's shown here in the vocabulary, but please keep in mind that its status is not approved, which means that the term itself has not been officially approved, officially approved by the vocabulary moderators to be used in the vocabulary. Now, if I click on it, I get this view here, which shows some of the more detailed information about the term. Information such as its definition, its data type, its broader terms, and these two IDs, the global ID and the local ID, which I will describe in a bit more detail later on. Additionally, I can also comment on the term, basically facilitate a discussion about it. And afterwards, I can also edit it. So here I'm adding a German translation to its definition and submitting it to the vocabulary. And this is the result. So you can see that the translation is shown there. Additionally, people can also add images to terms. So for example, here I'm adding an image of a cup grinding machine to the cup grinding machine term, just to make it a bit more not only machine readable, but also human readable. Now, following this short demonstration of Vocpopuli's features, I would like to move on to some of the details about what happens under the hood when a person uses Vocpopuli. Now, as I mentioned in the beginning, Vocpopuli is strongly based on GitLab. Right now, I want to show you what happens in GitLab when, for example, a person wants to define a new term, and let's say that that term is the term pen in the cup grinding vocabulary. Now, as soon as one initiates the term definition process, a new branch gets created in the repository which contains the vocabulary's terms. All edits done to that term are basically they get stored in that newly created branch. Then after some time, that term can get approved which means that it get the version of the term which got approved gets merged to the main branch of the repository on GitLab, after which people can basically add new terms to the vocabulary. Now, these processes are defined, sequenced, and identified using 5 IDs. I'm seeing right now that I'm a bit short on time, so I won't go into too much detail about them, but these IDs define the states of the vocabulary itself, as well as the terms themselves at each given point in time and after each edit to the vocabulary. Now, moving on to some more Vocpopuli features, which, as I said, are strongly dependent on GitLab. Vocpopuli offers, first of all, Git-based tracking, meaning who did what at which point in time. This is strongly connected to basically establishing the provenance of the vocabulary itself. And related to that point is also the possibility to annotate the generated repository as well as its provenance with the prof data model, so the prof DM data model. And additionally, we're also able to, we're not able to, the vocabularies themselves are stored as SCOS ontologies, which is a standard for thesauri and vocabularies, which facilitates the conversion of the vocabularies into ontologies. And that's just one of its benefits. Just as a final point, a summary to my talk today, and mostly to Vocpopuli. Now, Vocpopuli, as I said in the beginning, is a tool for collaborative vocabulary management and development, not only of vocabularies, but of fair vocabularies. It serves as the entry point to digitalization, meaning that it can serve as the entry point to laboratories who want to digitalize their data with the help of electronic lab notebooks, for example. And it is also a step towards scalable machine learning. Last and definitely not least, these are all of the people who take part in the development of the Karlsruhe Lab framework. And that's everything on my end. Thank you everyone for the attention. Sorry for taking a bit more of your time, and I'm looking forward to the questions.
Okay, thank you very much. Ebru, you're up. Thanks. We are a little bit short, but that's fine. So thank you all.
Okay, I guess now I can start. Great. Okay, after the beautiful fair data presentation, I will turn the topic to nanoscale superlubricity and be more experimental. But first, let me quickly introduce myself. My name is Ebru Cihan, and I'm currently a postdoc at the Technical University of Dresden. But in the context of WeSST today, I would like to talk about the results of my previous work on the effect of direct phase transition on superlubric sliding. So let's get started. Nanoscale superlubricity is just one of the amazing phenomena discovered using atomic force microscopy in friction measurements. It is characterized by the ultra-low friction observed between atomically flat and incommensurate surfaces through collective force cancellations without wear and plastic deformation during relative motion. Theoretically, if the two flat contact surfaces are incommensurate, there will be no interlocking state between the atoms, and as a result, the atoms will slide easily over each other, resulting in very frictional forces. And we can explain it in this way. As the contact area and thus the number of atoms in contact, or the sliding interface, increases, the potential energy barrier per atom will decrease, and the atoms will manage to stay at a higher level of the energy barrier. And this naturally means that sliding of atoms becomes easier. At this point, it is very important to systematically analyze this phenomenon of superlubricity. And for this, for this analysis, we can or we need absolutely well-defined contact areas. So an alternative tool for this purpose would be to use nanoparticles with well-defined contact areas, which we can manipulate using an atomic force microscope tip on a flat substrate. Because then this will allow us to analyze sliding friction as a function of contact area or number of atoms at the sliding interface with a scaling factor of gamma. So for well-ordered crystalline nanoparticles, this scaling factor gamma is calculated between 0 and 0.5, depending on the shape of the particle or the level of the commensurability between the surfaces. For randomly ordered amorphous nanoparticles, this gamma should be well-defined as 0.5. And this clearly indicates that less effective superlubricity is expected for amorphous structures. Previous experiments with crystalline gold and amorphous antimony nanoparticles confirmed this theory very well. That is, a different efficiency is demonstrated for crystalline gold nanoparticles where lower friction is achieved. This result is actually good, very good, but not sufficient. For an atomic-based explanation of superlubricity, because it has been demonstrated only for different type of materials. In other words, we still have an open question regarding the chemical nature of the interface, and that question also needs to be answered. So this question will be the starting point of this work. Namely, to investigate the atomic origin of superlubricity, we also need to analyze the same material in two different phases. And of course, we can achieve this through a direct transition from one structural phase to another by heating, for example. For this, we chose antimony nanoparticles because from our previous experiments, we know that we obtain amorphous antimony nanoparticles as a result of thermal deposition in our ultra-high vacuum chamber. And we also know that it is theoretically possible to convert the amorphous antimony to crystalline antimony by heating. So for this purpose, we first produce our antimony nanoparticles in our ultra-high vacuum chamber by thermal deposition, and then we transfer the sample to the atomic force microscope without breaking the vacuum for further manipulation experiments. As you see, the antimony nanoparticles on graphite here. This is a general overview of the antimony nanoparticles after deposition on graphite. For further manipulation experiments, we transfer the sample, as I said before, to atomic force microscope. And then the nanoparticles were laterally manipulated on graphite at different temperatures between 300 Kelvin and 750 Kelvin. So all nanomanipulation experiments were performed as a three-step process. To avoid skinning induced movement of nanoparticles, the sample was first imaged in non-contact mode, and then a nanoparticle suitable for manipulation was chosen. Then the AFM tip was placed directly next to the nanoparticle, and the system was switched to contact mode, and then nanoparticle manipulation was performed laterally. After the manipulation, particle displacement was confirmed again in non-contact mode. So here's an experimental data where these are the AFM images showing nanoparticles, the location of nanoparticles before and after the manipulation. And here is the tip, and here is these AFM images. And then this is show the lateral, the friction signals during manipulation. AFM gets in contact with the nanoparticle first 150 nanometer, where we also see a sudden increase in lateral force signal, which is the static friction peak. And then immediately after that, the particle begins to slide, which is the sliding friction. So this process was first applied for 3 nanoparticles, and the following results were obtained. The following results were obtained, and accordingly, we can talk about 3 different regions for the specified temperature range. First, friction decreases with increasing temperature, and then this decrease continues, and this decrease continues for a while, and then at even higher temperatures, it increases slightly, as shown in the yellow area here. And additionally, the gray background color shows here a typical phase transition temperature of nanoscale antimony, and the continuous lines marked in red and blue were calculated according to the thermally activated stick slip, thermally activated Proton-Thomson model, and they reflect different energy values for low and high temperature region. Due to time constraints, I will not go into further details at this time. So then, interestingly, this friction reduction remained constant here after the sample was cooled back to room temperature. We can see it easily with this red data points. And this made us think that there must be a reversal phase change in antimony. So to further analyze this, we performed additional manipulation experiments and manipulation experiments on a freshly prepared sample. And antimony nanoparticles were first manipulated at room temperature, and then at 500 Kelvin, and finally again at room temperature. As a result, these experiments confirmed previous observations. As you can see, friction is reduced by a factor of log2 when heats to 500 Kelvin. And this friction change is found to be reversible since the same level of friction is measured after cooling back to room temperature. So before I finish, let me quickly relate this friction change to the scaling of superlubricity. If we fit the data we obtained at room temperature before any heat treatment with a fixed scaling factor of 0.5, we can achieve a reduced scaling factor of 0.42 for the data we obtained at room temperature after heating. And this can be attributed to the increased efficiency of force cancellations at the sliding interface, which becomes more regular due to the amorphous crystalline phase transition in antimony. So with this, I'm come to an end. In summary, we try to show the effect of direct phase transition on superlubric friction. The last but not the least, these results highlight the importance of atomic structure at the sliding interface in the superlubric regime. With that, I would like to thank you for your attention.
Fantastic. Thank you, Ebru, and thank you for all of the speakers in this Flash Talks session. Round of applause. Sorry, let me do this. There you go. So now we have about 10-12 minutes for questions. Please feel free to ask questions about any of the talks we just had, both the speakers in the Zoom chat and if we have question in the main chat on YouTube. Yes. Is anybody on already?
So far, no questions on the main chat.
Okay, go on.
As I can see, but I have questions. Actually, it's all 3, and I will just ask 3 in a row. Like I'm giving very short flash talks, and then you can answer in a row, I guess. So first for Nick. So how you mentioned it's dependent on the use case, of course, to implement this in a lab. But I'm curious about like the interest you have gathered so far. I mean, I know this is very new and the publications are new, but this seems to be extremely useful, I guess. But then I have, in my experience, not all people are, very willing to share data immediately. So this is also something I didn't get maybe. So you can do this locally, I guess, and then share as much of the results as you want, or will this be uploaded immediately and accessible to everyone immediately? Then my question for Ilya would be about the similar thing, of course, with this this Git-based approach. If this is done, let's say, in a repository for each user separately, and then what happens if there are merge conflicts? And for Ebru, something I didn't quite get, when you in these colored lines you showed with the different regimes of the friction, these you said were fits to the data, or these were separate calculations based on the thermal activated PT model? And if that was separate calculations, which how did you choose the potential for that? Okay.
Let's start from Nick. Otherwise, it's going to be like a concerted answer.
Yeah, so that's why I wanted to make the distinction between open and fair data early. Fair does not mean open. Now it's the researcher's choice to make it open. Often it's not if they get funded from public sources, because I think it's only the ethical thing that if you're playing with taxpayers' money to give back to society and share your outputs, that's actually the ethical thing to do. And there is going to be a cultural change in that respect, and people's fears will probably be overcome. But as of right now, there are so many applications of fair data that don't just include open data. So I would say that that's just part of the story, the open part. And speaking about adoption, I have gotten pretty good feedback. It's usually the people that find us are the ones that are already conditioned to look for something related to data, and they've gone through the thought process of what is the significance of data. So when they come to us, they're already aware of the fact that they might need to do some of their data open.
Thank you.
Yes, moving on to me then. I hope I remember your question exactly, Michael, but basically, I don't think I had enough time to describe that in detail, but the way we go about defining these repositories and working with them is that each vocabulary, which is to say each research group, more or less, is given one repository in which they define their vocabulary. So all of the members of that vocabulary definition team, so to speak, are also members of that repository in GitLab. Now, the way we prevent merge conflicts is more or less the following. So I showed that picture, that slide with different branches for the development of each of the individual terms. All of the development done on the vocabulary is done in these individual branches, and it is done in a way which, so the workflow itself is programmed in a way in which merge conflicts aren't really possible. So on one hand, we only edit these branches. The main branches themselves, the main branch itself stays constant, and it contains the terms which have been approved in the vocabulary. Additionally, these edits aren't done in a single file, but rather we generate different files for each version of each term in its development branch. And these two parts basically allow us to define and develop vocabularies in terms without worrying for merge conflicts, because the how should I put it? The most severe issue which could arise is that two people submit a terms definition at exactly the same time. So literally at exactly the same point in time. But even then, this would only lead to two files being generated in the branch, in the development branch of that term, which again doesn't really lead to merge conflicts. So yeah, that's the technical explanation. I hope it managed to answer your question.
Thank you.
Yeah.
Cool, thanks. Ebru, do you remember the question, or Michael, you want to do it again?
Actually, I couldn't hear Michael very well. Therefore, I would be happy if he can repeat. And a bit loudly, maybe, sorry.
Okay, so my question was, the colored lines you showed, they looked like fit to the data in the different temperature regimes. So for the crystalline and non-crystalline.
Okay, the last presentation, okay, slide maybe you mean. Okay, yeah.
So those were, I didn't see if those were like fits, like just trend lines, or if you mentioned something about thermally actuated Prandtl-Tomlinson model. So I wanted to solve if these were calculated lines, and then how do you get the potential for this model?
Okay, I see. Okay, I understand your question. Thank you for the question. First, actually, I said fit. You're right, but they are exactly calculated lines. I mean, we first calculated depending on the energy barrier E0 value of each particle. I mean, each antimony. We first calculated gamma scaling factor, and then we use this number to make these lines as a fit on the graph. They are calculated values, yeah.
Okay, thank you.
We probably have maybe 4 minutes for another question. We don't have any question in the chat. I do have a curiosity, a technical curiosity about creating this metadata or establishing the metadata, but thanks to the question from Mikael, actually I understood a little bit more. I'm curious about things like for experimental data, so for metadata associated to experimental approaches of various types, you also do define, I don't know, units, error bars, all of these things. Is there a unified way to do so? Like, for instance, you insert the value and then there's an automatic way of unifying the units, so it's all self-determined, self-imposed.
Maybe I can take this. So I would say it's both. It's up to the users. In our case, we did define our units, and units are tricky, especially in tribology. I mean, we don't have units like a named unit for wear, for example, or a wear rate. So you have to be very careful with units. But the strength of ontologies is the fact that you can relate what you mean to some other definition. And we have this in Vocpopuli as well in vocabularies when you put a synonym. So if I if I use the German word for friction, you can put that as a translation and it immediately relates to that. And if somebody has defined it in the other language, that definition from the other language gets carried over in your definition automatically. So that's really the strength of big data and linked data. And the point is that you just have to put it semi in the right way in which we try to guide the user to put it in so that the data finds its place automatically.
Okay, I see. Okay, there's one minute for one question. What is the question?
So the question is in the chat from Research Space. Question for Nick and Ilya. Very quick answer, please. To what extent are the controlled vocabulary and ontology frameworks you have created tribology specific, and to what extent are they generalizable universal?
I usually say that if you manage to digitalize tribology, you're fine on all other sciences. So they are general.
Yeah, I concur. Very general. So yeah.
Okay, that was quick. Well, thank you very much for all of the speakers to help us out to be in time because of these initial technical problems. We were a little bit off, so thank you very much. I think we can do one remote round of applause for the Flash speakers, as I decided to call them. And we now move to what we were supposed to have a break, which we're not going to have this time round. And I'm very happy to actually introduce the last speaker of this section. The next speaker is Dr. Marius Stan. So Marius is a scientific consultant with expertise in multiscale modeling and AI. Before retiring last year, he was a senior scientist and leader of intelligent material design in the Applied Materials Division at Argonne National Laboratory, as well as a senior fellow at University of Chicago and Northwestern University. So Marius and his group has been using AI and high-performance multiscale computer simulations to understand and predict physical and chemical properties of complex systems both for energy production, energy storage, electronics, and a number of applications like national security as well. So the group also used AI to optimize complex manufacturing process, such as 3D printing and flame spray pyrolysis. Marius has extensively published in the scientific literature, holds several patents, and is even currently working on a book on modeling and simulation. So very happy to have him here. Today's title for his talk is Recent Advancements in Artificial Intelligence and the Impact on Tribology. Please, Marius, go ahead. And thank you for having waiting longer than you would have wanted.
That's okay. Thank you for inviting me. Just want to make sure that you can hear me well. Is that well enough? Okay. So I'll go on with sharing the screen. All right. Do you see my first slide? Everything okay? All right. So when Norbert and I first interacted about this conference, we had some back and forth messages, and in the end converged towards this idea of discussing a bit more about the history and the progress in artificial intelligence, and then giving some examples from the work in our group at Argonne and at Northwestern and University of Chicago. And I will end with considerations about the impact on tribology. Although I'm not an expert in that field, I rely on your participation and help in seeing if elements of artificial intelligence can be used and can make a positive impact on tribology. Let me see if I can also have, yeah, I will just stop here. So a brief history of artificial intelligence. This is part of the book that was mentioned. I'm under contract to write a book on human and artificial intelligence, and this is going to be a section in that book. Of course, just to spark your interest, I'll give you some elements of the way I perceive the evolution of this technology. And it's maybe it's older than you may think. What many consider the start of AI is in fact a paper by Alan Turing from 1950, in which he posed the question, can machines think? He estimated that the answer to this question will come in maybe 5 decades, and he was off by 15 years or so, you'll see. At the time, Turing was working at the National Physics Laboratory in UK. If you've seen the movie The Imitation Game, the story of the Enigma machine, the way they deciphered the communication, encrypted communication that the Germans used during the war. What might be an even bigger surprise, it was for me, however, when I researched this field, is that shortly after 1952, 1957, two concepts that are familiar to us, and you've heard them mentioned in the previous talks, machine learning and neural networks, have been proposed. So these are not new developments. We are not in the midst of a new area of technology or of algorithmic development. It's just that for a while, the artificial intelligence research field went through what is referred as the winter of AI. It practically froze. The programs stopped. There was less interest, less funding. And why do you think that was? When I give this talk live, I usually interact with the audience and say, what are your opinions? And people come up with answers like, oh, there was no internet, there was no Google, there were not that many powerful machines, computational machines that could help. I do think that one of the main reasons was the overconfidence that the researchers who worked in that area had in their technology, and the fact that they overstated the power of artificial intelligence. You will see ads and headlines saying robots will clean your kitchen, will take your children to school, will do this and that, and it just didn't happen. So I will take away from this the fact that myself, first of all, but all of us maybe as a community should be careful with proposing the impact and the advantages of artificial intelligence in any field. We should be a bit more cautious. Now, 1997 marked a turning point in the attitude, the way the public embraced artificial intelligence, because it came as a shock that a computer defeated the world chess champion, Kasparov. That was really a shock for the human chess players, which was maybe doubled by the fact that, or enhanced by the fact that more recently AlphaGo also defeated the human Go champion recently. In between, we have a number of developments, the Watson machine at IBM, the personal assistants. Many of you are using Siri, Cortana, or Google, Alexa, and things like that. Now, here is the 2014 moment when Eugene Gossman, which was software developed by a Russian and a Ukrainian team, managed to pass the Turing test. It was, you see, 64 years after the prediction made by Turing that it will take half a century for a machine to appear to behave and carry a conversation as if it was a human. So what's going to happen next? So I'm taking a risk here, and some of you will hold me accountable, no doubt, saying that we will have, by 2025, proof that intelligent software is able to contribute decisively to scientific discoveries and technology developments. And furthermore, I make the prediction that by 2035, we will add a piece of software, a program, as a co-author on a publication. And I have reasons, and I can demonstrate that there is a good chance that this will happen. And we can talk about that if you are interested at some point. Now, just briefly, some of the recent developments in this technology before going to examples in material science and tribology. One of the most spectacular ones, perhaps, is the fact that in several cities across the United States, Los Angeles is one of them, even on the East Coast, we can have Las Vegas, we can have self-driving machines. Various companies are involved in developing this technology. They can pick you up from home and take you to the airport and bring you back. I'm not sure, I never traveled in one of them if they do small talk or carry a conversation or anything along the way, but definitely it's quite impressive. And of course, there have been problems. There have been a few accidents, some of them quite severe. But human drivers make mistakes too, right? Here's another example where a certain type of machine learning algorithm based on the reinforcement learning is able to play games of high complexity and win almost all the time. So if anybody plays online, like my son does, with people around the world and loses all the time, it's because maybe at the other end there is no, I don't know, Jim Johnson from Kentucky, but actually a robot or a bot, a software that is able to use this type of technology, including GANs, generative adversarial networks, and win at the games. The applications go beyond materials, go beyond physics and chemistry. I believe these very intelligent pieces of software are able to win now even in strategic situations such as war, actual wars, or conflicts between inside society. And another one that I found spectacular too, just a few years ago in Japan, a computer was able to propose to submit a novel to a contest without mentioning that this was not written by a human but by a machine, and passed the first round of screening. Nobody realized it was not a human author. However, it didn't win. It didn't even make it to the final. But to me, it's significant, especially in light of the Turing test, that the members of the reviewing committee thought for a while that it was a text of good enough quality to be promoted to the next round. So just few other things that may or may not impact your research field in tribology. Robots. I assume there are areas in tribology where robots are being used, quite sophisticated devices that are far from what we've seen in the past. They can move easily, they can react properly when pushed around, when tripped, find their balance, can recognize objects, find their way in various environments. Here's another one. We had a project at Argonne National Laboratory where a swarm of drones was used to supervise events, was flying above the Soldiers Field Stadium here in downtown Chicago, and looked for potential fires that might jeopardize the safety of the people in the stadium, or for conflicts, I don't know, scuffles, or somebody starting a fight that required the intervention of the security of the stadium. And let me tell you that they were, the drones were far better at identifying fires than human conflicts. Whenever somebody would trip with a Coca-Cola and spill Coca-Cola down the stairs, they tended to say, oh, there is something happening and we need to call security. Last example is a robotics school of fish, where each member of this team, let's call it a team, was able not only to analyze the environment at very far from their base, their home, but also communicate with other team members and make decisions in an autonomous way. They will examine the environment, decide if they need to go farther and explore more or withdraw, if they need a light or not to save energy battery. There was no contact between the school of fish and the research team until they returned. And when they returned, they provided a report, a comprehensive report of what they found. Now, you may imagine applications, various applications of all these aspects of artificial intelligence, but let's slowly return to the topic, the main topic of this meeting, of this conference. And I would say that we should think for a moment at the advantages and the drawbacks of this technology. And I'm putting this up front in the spirit that I mentioned, that we should not overstate the power of artificial intelligence. It's true that it can process data at higher speed, higher volume, even a higher variety of data types, far better than a human. It can work all day long, 24 hours a day, never gets tired, never gets moody. That's also interesting. It's a cold, effective, efficient partner in any research activity. There are, however, some drawbacks that have been pointed out. And then we have the believers. Maybe it's not a coincidence that the believers in AI are also CEOs or CDOs of large companies that create AI software. And the skeptics, such as Elon Musk or Stephen Hawking, who warned the community that there might be dangers associated with developing this technology. Now, I suggest to embrace the positive aspects and the power of artificial intelligence, and to convince you that there is a good path forward, I'll give some examples. First of all, this has been presented in previous talks by Luka and others. Artificial intelligence is a complex technology. What I would like to emphasize is that it is goes far beyond machine learning. I never use, it's just a preference, AI/ML. Machine learning is an important, a key component of artificial intelligence, but it's not the only one. As you will see in the examples I will present, computer vision is important, robotics, natural language processing that has been mentioned in a recent presentation. And then, of course, machine learning is nested in AI, and so is deep learning algorithms based on natural networks, part of machine learning, as it was pointed out. So instead of discussing in more detail the structure, I will give some examples, especially in the area of using different classes of algorithms in machine learning, computer vision, and a little bit about natural language processing. So first I invite you, and here we're going to put our technology to test and the broadband we have. I invite you to examine the video clip of a candle and tell me if you can see the flame changing, right? Everybody does? Is that okay? Now, you may not believe this, but our project started with the analysis of this image. We were wondering what goes through a human's mind when looking at this video, the clip. How do we make this determination that, for example, at the very beginning, the flame was stable, somewhere in the middle, it became unstable, and at the end, was stable again? I confess that I don't know exactly how I do that. I guess everybody who looks at that video clip can make the similar statement. Stable, then unstable, then stable again. How do we do that? I got no training in flame stability, but somehow, based on my life experience, I can make such a determination. Now, if we go to flame spray paralysis, a technology that involves putting chemicals in a flame and obtaining a powder with specific properties. I'm simplifying that too much, but I think it's enough to get the point. If we would look at, as humans, at the stability of these highly sophisticated devices and flames, it's not going to be that easy for us to make similar determinations. So the question was, can we develop the software? And not only a software, but also can we couple it with a high quality camera and analyze flames in a way similar to the one the technologists do? And can we do that with such detail and confidence in the result that maybe the software can help the technologists and maybe even take over some of the tasks that the technologists have? So the advantage of that would be that instead of having a human supervising these flames all day long, or in shifts, 3 shifts of 8 hours, we can have the software coupled to the camera make these determinations and maybe trigger messages to the technologist and say, hey, your flame is unstable or is going almost extinct. We need to do something. Can you do something? Or in the near future, trust the software with taking action, restoring the system to the normal operating system. Now, we did such an experiment. We used a large number of video clips and images. And first of all, asked experts, human experts, at Argonne National Laboratory, at Princeton University, and at the local universities in Chicago, to examine the video clips and tell us which ones they thought were stable, which ones they thought were unstable, and when was it that they could not make a determination. It was unclear, uncertain. And then trained using supervised learning, a class of algorithms that operates most of the time on labeled data, in the sense that we know what the features are, the algorithm is aware of certain characteristics of the system it's supposed to examine. We used approximately 80% of the data for training, and the rest for making predictions, video clips, images that have not been used in the training. For those who are interested, at the bottom of each slide, I have a reference to a paper, that one of the several papers that is relevant to this experiment, where you can find more information. But at the core, this was based on region-based convolutional neural networks, as available in TensorFlow. And now I hope you can see how these algorithms operate. And of course, the question is it the same as humans do? When I look at such flame, what goes through my mind? Do I look at the length, of the width, of the color, of the intensity of the light? What is this algorithm operating? Is it operating the same way as my mind does? That was an interesting question, I would say, which was not answered yet. Then we decided to use a different class of machine learning algorithms for clustering. This would be unsupervised learning. And in preparation of that, we used a principal component analysis to reduce the space from over 40,000 data points or coordinates to just 2 principal components. For those of you who are interested, we also looked at 3 and more, but determined that 2 principal components are sufficient. In this representation, various video clips appear in what to a human would be several clusters. Some of them in the upper right, upper left part, some in the bottom, others are in the lower and upper right part. And then we ask the algorithm to group them, to cluster it, to propose the regions where the algorithm considered that one can group the stable flames, the unstable, and the uncertain ones. You see, this is unlabeled in the sense that the algorithm doesn't know and doesn't care what these points represent. It's just interested in grouping them. It starts with a centroid, which is a black point, which maybe you cannot see, but somewhere in here for each area. And then goes around, brings in the points that are nearest to the centroid, and continues this process until it forms and proposes 3 clusters. And now I'm gonna pause a little bit and say, and ask you to think and estimate how good, how well the 2 algorithms, supervised learning and unsupervised learning, did in predicting the stability of the flames compared to the humans. Was it the supervised one with the data labeled and all the features of the flame, or the unsupervised one, which required far less training, but was quicker? And here is the result. Again, a publication listed down at the bottom of the slide. I hope it matched your expectations. if we assign the ground truth to humans' evaluation, we think humans are always right, and maybe they are, maybe we are. The supervised learning algorithm made predictions that were consistent with the humans' evaluations up to over 90%. Really good. But then remember, we had to train it for maybe a couple of weeks on hundreds of video clips and images. We had to label those, we had to give examples and counterexamples for stability and instability of the flames. We did a lot of work to make this algorithm make predictions that are so good. The unsupervised learning method, the clustering one, did well too, 73.6%. I would say that's not bad at all. And of course, the question came up, when is it worth to put a lot of effort in training a complex algorithm of any kind, but a machine learning one in particular, to gain high precision and accuracy? And in what situations we can live with an algorithm that is quicker, doesn't require so much training, but makes good predictions nevertheless. So that's something to think about. And I guess for each project, for each application, there will always be a choice regarding the type of algorithm that's most beneficial in terms of the time, the effort, the energy, the funding, the team that one is willing to put forward to address, to make good models and predictions. Now we do have a good result, good news to share with you. This is the control panel of that experiment, flame spray pyrolysis. And I'm gonna run a recording of what was at the time a live broadcast of the way this intelligent software controls the entire process. You will see in the lower left part the actual image coming from the burner, the flame. You'll see various control elements, temperature, oxygen level. On the upper right, we have that blue dotted line, the distribution of particles in the powder, which is the end result of this chemical process. And other information that may not be so relevant for this discussion. I'm showing this just to demonstrate that it is possible to have a software that analyzes somehow through vision, memorization, decision-making, learning, a rather complex and dangerous. It's chemistry at high temperature, chemicals in the flame, methane, explosives, and it does it with such good results that the technologist is now using this software to restore the process to normal conditions, to even design experiments and create powders of a specific distribution and so on. So I imagine that one day there will be a manufacturing plant that maybe uses 200 such experimental setups, and there is an intelligent software that monitors all of them and takes corrective actions, even in the most difficult situation. This is the team of researchers. They are humans after all. No code, no software can do anything meaningful by itself at this time. We have chemists, we have mathematicians, data analysis specialists, CFD experts, and we had a student from Princeton 3 years ago who spent 3 months with us. The student did so well in proposing elements of the project, analyzing the data, writing code, running the code, that not only that we decided to add her as a co-author of the paper, but she is the main or the first author of this paper, which is quite something, I would say, for a junior undergrad, right? And I'm telling you, we thought long and hard if we should include as a co-author the code itself, the Python code that we wrote to accomplish all these elements, and decided not to, for the reason that the code displayed intelligence, a lot of knowledge, energy, but no elements of creativity. We didn't get any new idea, any great suggestion for the path forward from this software. But I'm confident that not long from now, a piece of software will become the co-author of a paper, and it could be, my estimation, in the area of discovering materials with spectacular properties that humans have been searching for a long time and haven't been able to find. Okay, so briefly another example, just to illustrate that AI can be used not only for optimizing in real time complex synthesis, manufacturing processes, but also for discovering new materials, for improving, for screening compositions and structures to create materials with better properties. This is an example not related to tribology, but I would say that a similar approach could be used to optimize properties that are key to tribology projects and experiments. In this case, we were looking at hafnium oxide, for the purpose of improving the performance of memory in computers. And here is one slide that is really busy, but it's a condensed information bucket, if you want, that one can use to understand the process. This was in collaboration with Gabor Csányi, that was mentioned by Luka at the very beginning of the session. Indeed, we worked with him on using machine learning to improve the interatomic potentials. But the machine learning played a larger role here. We also coupled machine learning with Bayesian analysis and made determinations regarding the uncertainty of various properties of this material. Furthermore, we use active learning to optimize the investigation, the screening of the space, property space, in real time. As you can tell, there are both the supervised machine learning as it relates to regression was used to create optimal models that link, for example, density and other properties to temperature and the composition, but also unsupervised machine clustering algorithms that help us identify regions of the hyperspace that are associated with the best properties. Again, I invite you to read the paper if you have the time in PhysRev letters, also in the Nature Partner Journal dedicated to computational material science. It has been mentioned several times that AI can also help accelerate computer simulations, which was the case here, quite a spectacular acceleration. We managed to do 100 times better than classical DFT with similar accuracy. This is not, I mean, it's not 2 times, 5 times, it's 100 times better. In the area of optimizing the interatomic potentials. 20 years ago, I would do that by hand using modified embedded atom methods and so on, and it would be a couple of months for Mike Vasquez and I to use our knowledge and some black magic to determine the optimal interatomic potential. Now one can do that in a couple of days, sometimes even in a few hours. This is spectacular, reducing the human time and effort necessary to optimize force fields, interatomic potentials for DFT, for molecular dynamics, and so on. So this resulted in a better material for computer memories. Now I'm gonna wrap up by mentioning what I found while researching for applications of artificial intelligence to tribology. I'm no expert, I will let you judge the value of these, but I thought of giving just a couple of examples. One of them is designing polyethylene composites using elements of artificial intelligence. This must be an important project, not for me to judge. What I liked about this project in particular was the way they used deep learning coupled with genetic algorithms to create relationships between Young's models and the tensile strength that are optimal for that particular application. No one can do this by trial and error or cook and look, as I used to do decades ago. Try different compositions. In the case of composites, try different orientations, different ratios between the components until we find an optimal relationship between Young models and tensile strength. But the help that AI provided cannot be neglected. They were able to do this quicker in a more comprehensive way. And the result was an actual improvement in the properties of that composite material. So I thought that was a good example of how AI can help in this area. And here's a representation, a diagram that shows how similar these approaches can be. If you remember in what I showed you about the splitting frame paralysis, we will use experimental information and computational results, synthetic data from DFT, molecular dynamics, and so on, and then had an integrator, if you had an engine that used machine learning and computer vision and natural language processes to optimize the whole process. One can use supervised or unsupervised learning for classification, regression, clustering. Now, the parameters they give here as example in the input training data, solid properties, surface properties, lubricant, as well as in the output training, film thickness, friction, are examples from this work that I'm referencing. But I invite you to think of your particular project in the area of tribology and say, oh, what would I put in this box here? What would be my input properties and training data sets? What am I going to collect from experiment? And what's the output that I care about, the parameters that I care about? And is there anything specific that we could list in this central box that will help optimize the entire system, something that will work in particular for a project that you are interested in? And if you feel like that it would be good, useful to discuss about how to set up this environment for your particular projects, let me know. Again, I may not know much about tribology, but I do have some experience with creating methodologies like this one that involve elements of artificial intelligence and multi-scale simulation methods. Now, if you think that's interesting enough, shoot me an email at mariustan365@gmail.com. That's my address here in Chicago. And we can talk about many, many things. Some of the ones that I mentioned, that AI is in fact a technology that has been around for a long time with more or less success, and it's more than machine learning. That we have various classes of algorithms that one can use, and each of them has its strength and weakness in addressing specific mathematical problems, but also physics or chemistry projects. I am very proud to restate that we had created a program that is intelligent enough to assist the technologists in controlling in real time a complex chemical synthesis, and maybe even can be entrusted with running that process by itself. And the fact that we can use AI, elements of AI, again, not only machine learning, to explore various structures, various compositions, various temperature, pressure fields, and discover and create, design better materials. That's, I think, something that cannot be neglected. No, I didn't know what to say useful and meaningful for tribology. I'm just expressing my hope that the community would embrace some elements of AI and combine them, couple them with what is already existing in matter, in experiment and computation, and make it such that it's a, how should I say, it enhances what you are doing right now. AI is not a competitor. I don't see it as a danger. On the contrary, I think it's a technology that can make our science and technology and our life better. So I thank you for your attention, and I'll answer any questions and if there's any comments you might have. Thank you.
Thank you very much, Marius. That was very, very, very interesting. Personally, I learned a lot, not be directly in the field of AI. Are there any questions in the chat or by the audience or by the organizers?
So I don't see any questions in the chat so far. I do have a question, however, which I might ask. So very nice talk, I agree. But the question about an AI or some kind of software co-authoring a paper. I mean, I know that there are several people co-authoring papers that probably should not be co-authoring papers. If you look at the different definitions that journals and scientific institutions have, let's say, as measurements who should be on a paper and not. But I mean, if you put in an artificial intelligence, then you should put as an author every other software you use that is a little bit more complex, right? I mean, as long as, and maybe I'm missing the point here, but as long as you don't have any really creative input, isn't it just a tool like any other?
No, maybe a clarification is required. Of course, anybody can add the name of a code as a co-author and submit to a journal. There is nothing preventing you doing that other than maybe some restrictions at your company or university, or say you cannot add anybody on the publications. But what I'm referring to is a situation where such a paper passes the review, a peer review. And the software is considered truly as a meaningful contributor to that research on the same foot with the human participants. So I see that possible because, as you mentioned, one judges the contribution of each author of a publication, and we cannot have absolutely equal contributions from everybody. Some do more, some less. There are different areas there. And I see the fact that the moment AI codes demonstrate creativity, which to me is the ability of finding a new solution to a problem, something original that hasn't been thought out by anybody. That moment, we could add it. The way it is right now, the fact that it helps analyzing large bodies of data, the fact that it helps us do things faster is not sufficient, is not enough. But I see as a possibility that in a few years, a program will demonstrate the fact that it can discover, as I said, a new material or propose an original idea for improving a technology that, should the entity be a human, we would not hesitate in adding that entity to the paper. But because it's a program, we can struggle. I hope I explained a little bit, because otherwise there are people who did funny experiments. They added the name of their cat to a paper and submitted to a journal, and that was rejected and so on. I'm not talking about that. I'm talking about the meaningful contribution that we would all agree it's important enough to warrant co-authoring a paper, a journal.
Yeah, I think that was exactly the clarification I was looking for. The point that the creativity is needed, that maybe I misheard in the first part. And by the way, I just saw that Nick and Ilya had to leave because they have another meeting, so I again apologize for
but it's really, thank you, Marius, for his encouraging perspective, he's saying in the chat, which is actually how I feel as well. Maybe I have a quick curiosity. I don't know if I missed that, or I just so when you were talking about humans versus supervised versus unsupervised, were those trained humans? So the human, regarding the part that you were discussing, describing about the flame, and you were saying that you compared human versus unsupervised learning, and supervised learning and supervised learning. I was wondering if the human part was a trained human or it was...
No, so we had 11 experts of all ages, students, professors, scientists, all of them with some understanding of combustion. Right, I'm a physicist and a chemist. My PhD is in chemistry. I understand combustion. So none of us was an expert, for example, in the computational fluid dynamics of these. So we were more interested in their gut reaction, their instinct. What did they think, without asking them to do a similar analysis? So there were no instructions given. For example, look at the intensity, look at the color, look at this and that. So so the answer is they did not go through a specific training. That might have biased their...
some bias, yeah. Somehow. In some direction. But maybe they counter balance each other depending on what kind of education or experience they might have had.
That is...
Okay. Sorry for the interruption. Who else has questions for Marius? Someone else? I might have one last curiosity if we have time, or if you guys want to go. I have one last DFT oriented, because I am a DFT person, and every time I hear that, then I tend to ask myself. So in the paper with, I guess this is Gabor, in the paper with Gabor, so you mentioned briefly that you found a similar accuracy as DFT. Can you be a little bit more specific for a similar and what DFT?
Right, so we were looking at using machine learning to create an interatomic potential that has a quality that is similar to the ones that are being used currently in DFT for hafnium oxide, for example.
Okay,
and
for
specific. And looked at properties such as energy of formation, cohesive energy. We looked at evaluating the lattice parameters predicted, equilibrium lattice predicted by the two. So during that comparison, we thought that, okay, the results are similar enough in terms of EV per atom, in terms of angstroms. And here is where I'm placing similar accuracy and confidence in the result. And then we found that, as I said, it took us far less time to reach these type of results that were used in this comparison. If we think of how long it took to various research teams to propose interatomic potentials for hafnia. So that was the basis for the for the statement. Can we produce similar results with the same accuracy and precision using this technology?
Wow.
Now, I'm just going to add that there might be, and this goes to all the talks before. One of the things with machine learning is that it's not fully understandable. It's not fully transparent how these algorithms work. And we often don't get any explicit analytical relationship between the input and the output. It just works amazingly well. In some sense, it's a black box. And to me, it's a return to empiricism. And here's another question for anybody in science. Do you care about understanding the physics, the chemistry, the fundamental laws of the nature, or it's more important to get an accurate results quickly? So I'm a physicist and a chemist by training. It pains me to acknowledge that often I don't know why the code I wrote performs so well and what's behind that, and how can I relate that to the fundamental laws of science. And it's a conundrum. I don't know what to say more about this. It's something that I struggle with. Maybe others have resolved this issue.
Well, that's something to think on, especially if one starts to incorporate these tools more and more in its own research or her own research. We're gonna find ourselves having to make a decision on how we feel about this. Again.
Indeed. So to your comment before, if you have a Lennard Jones in the atomic potential, you know what every coefficient means or everything.
Yeah.
Means. If you have a prediction made by the machine learned interatomic potential, is as accurate and precise, but we don't have any explicit form. We don't know what goes in that, how that relates to the physics, to the interactions.
Yeah. Okay. Well, thank you very much for everyone who participated to this session, from Marius and all of the speakers that were here. So I would give one more virtual round of applause, as Norbert has already done. I just want to conclude by saying that we're going to continue our seminars on the 10th of October, where we have our next session. On that day, we have Maria Clelia Righi from Bologna, and we have Noah Maram for Carnegie Mellon University in the US. And I feel very good about the session we have today, because our intent was to start introducing the main tools and advances in machine learning and AI and big data environment, like subjects, and so this was a good way to start off with these web seminars. Now the idea is that maybe we all have much more understanding of these tools, and in the next seminars we're going to have more tribology oriented applications of the very tools we have discussed today that Luka and Marius have so brilliantly sort of told us about. Hope you enjoyed the talks today, and I hope I will see you on the 10th of October, and then on the 14th as well. There's also, I don't know if Mikael and Norbert want to also say something.
I want to quickly mention that I enjoyed this really much. I completely agree with Martina in her assessment. I think the talks were amazing. Thanks to all the speakers. The audience interaction maybe was a little bit lacking. Nevertheless, if I can trust the YouTube statistics, we had more than 100 viewers on the stream, which is nice, I think. And yeah, we will discuss later with the authors, maybe not the authors, but the speakers per email, if we will leave this up as a video on demand, if we can keep the video on YouTube so other people can rewatch it. I mean, maybe Friday evening, at least in Europe it's evening. It's not the best time, but it was necessary to make this work with everybody's schedule. And yeah, I hope we see each other again at the 10th. I hope that the speakers will be there as audience. We'll ask some questions in the chat.
Great.
And it was a joy to be there for you. I'm apologizing again for the sound issues that were resolved with a very easy step of restarting the program.
Something to keep in mind, restarting always.
And yeah,
okay.
Maybe Norbert wants to say
Thank you all. Have a good weekend.
You too.
Thank you.
Bye, everyone.
Goodbye.
Thank you again. Bye.
Thank you again. Thank
Goodbye.
you, Andrew.
Okay, then I will stop the stream.